if I go to a system software programmer or a computer scientist and tell him that, oh, I have this awesome framework, why don't you rewrite your 1,000 lines, 10,000 or 20,000 lines of code? He'll say, come again next year, I'll think about it. So nobody wants to do it really. So the second question they might ask is, but can I use Charm++ without making changes to my code? Or can I use Charm++ partially to get the concrete evidence of performance gains I may get if I move to Charm++? Or can I improve performance of some of the kernels which I think are more conducive to Charm++? Or they may ask, can I do a chunk by chunk transition to Charm++ from my current legacy code? And our answer is yes. So I'm listing the proposed paths which we suggest people may be able to take if they want to use Charm++ without totally jumping into Charm++ RTS. So first, if you have an OpenMP code, then the answer is Charm++ is not a new language. The code is written in C++. So all your existing code should work as it is. So just take your kernels and make the calls from Charm++ to them, and that's fine. It will work. However, if you're an MPI application writer, it's not that simple. We propose two approaches for them. One, you can use adaptive MPI, which is our own implementation of MPI on top of Charm++, or you can use interoperability feature of Charm++ to use some part of code in Charm++ and the remaining can stay in MPI. For the remaining paradigms, we do implement front-end APIs as need arise. For example, we still have an ARM CI API existing that resides in Charm++ and is tested every night for that matter. So focusing more on the first path, which is using adaptive MPI, the question is, what is adaptive MPI? It's nothing new actually. It's just our implementation of MPI standard. It's like if AMPI is one of the implementation of MPI, OpenMPI is one of them. So AMPI is our way of implementing MPI, but with some useful additions. So so one thing which we have been talking about is that over decomposition, as Sanjay mentioned, is fundamental to Charm++. So we infuse the idea of over decomposition to MPI by treating MPI rank as virtual processes which execute in their own user thread space. So from a Charm++ RTS perspective, it sees each of the MPI ranks or the virtual processes as a char of a char array that it is controlling and scheduling. So the figures look something like this. From a user perspective, he's still dealing with the blue, the dark blue or the purple boxes, which are the MPI ranks. But the Charm++ RTS views them as chars, which are placed on different processes, and it's going to be scheduled them one after the other as the need arise. Underneath, what we do is, let's say if you're making an MPI call and you call MPI receive. MPI receive cannot proceed till you receive the message. So what we'll do is, the MPI Charm scheduler will say, okay, since you can't proceed, why don't you go to a sleep state, and meanwhile some other MPI rank which is residing on the same core can proceed. And we do we apply similar strategies to other MPI calls like send or other collectives and so on. And that's how we implement MPI on Charm++ in an asynchronous manner. But that is not it. Like, we have some extra augmentations to the MPI interface which we have implemented to make sure that users can make use of some other functionalities. So the most important of them is MPI migrate. So as has been mentioned earlier, Charm++ supports load balancing and object migration. And since we are implementing MPI ranks as objects, we would like to provide migration facilities to MPI programs. So this is just a call for that. If a user calls MPI migrate, which is a global collective, Charm++ RTS underneath will conduct load balancing and migrate processes if necessary. The next call which we implement is called MPI_checkpoint. This is a way to checkpoint your current state, the current state of an MPI rank to the disk. And a corresponding call is MPI mem_checkpoint, which is a way to checkpoint your current MPI state to memory. So these two calls combined with the fault tolerance framework that Charm++ has can make any MPI program fault tolerant while running using AMPI. In addition, we have had non-blocking collectives which are also part of MPI 3 standard for a long period. So these are the MPI_I star operations which are recent additions to MPI. So these are the basic additions to the MPI standard that we provide with AMPI. However, when you're running a code in a multi-threaded manner like MPI, so the user has written the code assuming that it's going to run in only one thread environment. So he has global variables. He's not aware of the fact that Charm++ may be using it in a multi-threaded manner in which the global variables might be shared across thread. And that causes some problems to us. So to handle such problems, we have an implementation of memory allocation, which we call isomalloc. So the purpose of isomalloc is that is to intercept all the memory calls made by the user using our library and map them in our threads virtual space so that no two MPI ranks share a virtual address space. So when a process wants to migrate, we migrate the entire virtual space with that MPI rank with itself. As such, so when you are migrating from one process to another, there is always guarantee that you would never have any conflicts. And to handle the global variables, we have a soft global scheme in which we make use of the ELF format, which has a separate GOT table to access a particular global variable, and that one is used, and that data migrates along with the isomalloc data that was written earlier. However, if some machine doesn't have isomalloc or swap globals, then the approach we suggest is one, to avoid using global variables, or you can encapsulate your global variables into local variables and pass them along like a lot of recent MPI code does. And if you don't have isomalloc, then if you're migrating, you also need to pack your ranks. So isomalloc is a It's a way in which user doesn't have to perform any action. So, but if you don't have isomalloc support like on Blue Jeans, the user has to write his own pupper functions which will pack MPI ranks, and then he can transport it. Our aim with AMPI is to enable execution of any MPI code as AMPI. And the roadblocks, as I just mentioned, are global variables and how to perform migration. However, we have achieved reasonable success with running MPI based code. BRAMS, which is the Brazilian weather code, Brazilian weather modeling code based on RAMS, is probably the biggest success of AMPI that we have. We also ran ISAM, which is a integrated science climate assessment model. And then we have run all the NAS parallel benchmarks using AMPI without any code changes. And recently we have also run Mentivo benchmarks, Lulesh, and I'm going to show some of the results in the next two slides. So this is a run of the BRAMS code using MPI in which only one process runs per core. So this is a usage profile. On the x-axis is the process number, and on the y-axis is how much percentage utilization of each process was there. So as you can see that the average utilization in this case is around 35%, and for some processes it goes till 60%, but for a majority it remains very low. BRAMS is a communication intensive code in which a lot of MPI receives do cause a lot of waits for those MPI ranks. If we shift this code to AMPI and include decomposition, over decomposition, so we can overlap the communication cost with computation cost, and we receive figure which is on the right hand side. So as you can see that we have increased the utilization from an average of 30 to 35% to something like 55%, with some of the processes now being 90% utilized. Add to this load balancing and we get this. Now the figure on the right shows the average utilization or the utilization profile if BRAMS is run with in an over decomposed environment with load balancing being done. We are able to consistently get an average utilization of 85%, and some of the processes are able to are utilized for almost 100% time. The next example is of HPCCG. HPCCG is part of the Mentivo mini apps suite. It performs a conjugate gradient on an input sparse matrix. So incidentally, this is some run I did yesterday night. So I was able to download HPCCG right from the website and make 0 changes and able to run them as AMPI. And what results I got was this. These results are on small numbers, 128 cores to 1024 cores with y-axis as a performance. What I observed was using MPI and AMPI, there was no difference in performance. We were able to get the same performance with MPI in comparison to AMPI. I tried over decomposition here, but it didn't help me. So the reason there was HPCCG by default deals with matrices which are uniformly whose non-zeros are uniformly distributed. So essentially, when you start the code, you pass the number of rows each processor will have, and each row of them will have a fixed number of non-zeros, which is uniform, and there is no load imbalance. And the communication fraction of this code is very small in comparison to the computation part, and hence these results. So what I did was, just to satisfy my curiosity, is I made those matrices non-uniform across rows. So I made some of them have zero non-zeros in a row, sorry, not zero, but one or two non-zeros in a row, and some of them to have the initial pattern. Using that, what I saw was this. MPI still gives the same performance, that is, it was still taking 0.5 seconds per step. However, with CHARM's over decomposition and load balancing, I was able to reduce the communication time per step to 0.4, which is a 20% gain without making any significant change to the code. The only thing I had to change was add a MPI migrate at like step 50, because the code doesn't change its pattern over time. I can just do migration once, and that's all I need to do. In addition, what this helps me to do is it makes this code fault tolerant now. Since I can checkpoint it and restart it at my will, this code is no longer susceptible to any fault node failures. These are the two examples which I've given. We have obtained similar results with NAS benchmarks and some other Mentivo applications. From here, where are we going with AMPI? We are trying to improve the efficiency of AMPI. One criticism which we have had of AMPI has been that the ping pong times, or the if you perform really small operations, it might have extra communication overheads. So that is one area we are trying to improve, and we are trying to implement newer algorithms for collectives, because MPH and other MPI implementations keep pace with the latest in the collective world. We have lagged behind a bit, so we are trying to cover up on there. The second thing we are focusing on is to have an optimized support of AMPI and BlueGene queue. So BlueGene queue don't support mmap over the whole virtual region, which essentially means we can't use isomalloc there. And if you can't use isomalloc, that takes away a lot of freedom from you. That means if you want to support migration and run multiple threads, you will have to write your own puppers. So we are trying to find an alternate way, so that we can avoid all those things and make users' life easy. And second is, it doesn't support swapping of globals, so we are working on finding an alternate way there. Pupper is the CHARM's way of packing a particular object. So if you want an object to migrate from one place to other, the user has to write a function which will pack the essential entities, which CHARM plus RTS can call, pack the object, and go migrate the object, and then unpack it and re-execute and continue with the execution. So this is one way of doing AMPI code, or using CHARM++ with MPI code. But some users are less lazy. They want to write some kernels in CHARM++ and then want to make use of it. For example, if somebody has an application which does sorting, and we have a highly scalable sorting library in CHARM++ based on an old paper, and somebody wants to make use of it, the question is, can he do it? That's where approach 2 comes into picture. It allows chunk by chunk transition of codes to CHARM++. The steps are, you identify the kernels that you think will perform better with CHARM++, implement them with CHARM++, and then you just make calls to CHARM++ from your MPI based code, like you're making calls to any other library. CHARM++ in this case resides in the same memory space as MPI. It will perform its necessary initializations and resource procurement, but nothing beyond that. So you can just pass your memory locations as it is without incurring any message cost or anything of that sort when you are calling CHARM++ call, when you're making CHARM++ call. The control transfer between CHARM++ and MPI will be very similar to what will happen if you call something like a parmetis call code or a FFTW call code from your MPI library. For it's a function call basically. So charm is also being treated like a library where the control transfers to charm and comes back. We support interoperability in 3 particular modes. The first mode, which we call time sharing, is the mode in which we say that for some fraction of your application run, the entire set of processors will be running MPI, and for the remaining fraction they will be running charm++. So in this figure, MPI control is represented by the hashed lines, whereas charm control is represented by the filled block. So this mode is supported in MPI-based builds of charm, PAMI-based builds of charm, Gemini-based builds of charm. The next mode, which we call is space sharing, in which we divide the entire processor set into two or multiple smaller sets, and we provide the user this option that for some of the sets you can run them as MPI codes, and for the remaining set they will be under charm's control and will be doing operations as desired by the user. The third mode, which we call as the combined mode, is a mixture of the first two. So basically you can do a space and time sharing simultaneously and make calls to charm, go back, do some MPI work and come back and those sorts of things. So having known this, the next question, the obvious question is, what do I need to change in my charm code to make it interoperable? The answer is literally nothing. All you need to do is add an interface function which will invoke your main program of charm. As in, if you're doing, let's say, a sorting, you need to write an interface function which will call the sorting on char array. This function call is important because that is what will be called from the MPI code. So how would your MPI code look like? Your MPI code would look like something like this. You begin execution in the user main, you perform initialization and application initialization, then you create a subcommunicator which charm will use, and then you call charm init with that subcommunicator. And so charm will know that it's supposed to only work on those particular set of processes. Then as many times as you want, you can perform MPI based communication and application work, call charm libraries, go back to charm, go back to application and so on, and eventually you exit charm++. A concrete example would look something like this. You call MPI init, you do some work, and then you call MPI com split. Here I'm splitting based on your rank. If my rank is odd, I will belong to one kind of charm communicator. If my rank is even, I will belong to another kind of charm communicator. And then based on my rank, I either call a charm library or I do MPI work. Or I can just make a call to a charm library and all my processes will do charm work. However, the two sets will still be living in two different charm instances and they won't talk to each other. So this is how basically we propose that charm++ and MPI interoperability should be used. From here, where are we? Oh, so before that. So what are the use cases that we have found so far of charm++ MPI interoperability? We have demonstrated its use case in the HPC challenge submission with F50 benchmark last year. We have implemented a scalable sorting library based on a paper at IPDPS. We also have an efficient collision detection library that is in an interoperable shape. And going on in future, we are planning to enable space and combine sharing to other platforms such as MPI layer, such as PAMI and Eugenie. We are working on development of other interoperable libraries such as graph algorithms, efficient solvers, and we are hoping to integrate performance analysis of interoperable code using projections for both MPI and charm++ code. That's all I have. I'm open to questions now.